Hello. So, in the last class we have learnt explicit multi-step method. So, when do we say it is explicit? Suppose in order to compute value at n plus 1th stage, if the process is asking k past points, okay, that means n, n minus 1, n minus k plus 1. So, then we say it is explicit multi-step method. Okay. So, now in this lecture we are going to discuss implicit. So, when do we say it is implicit? As I mentioned before, to compute value at n plus 1th stage, if the processor on the right hand side demanding the value at n plus 1th stage. So, then that is called implicit. Okay. So, let us see how we can derive implicit expressions. So, implicit methods. Okay. So, y dashed is f of x y. So, this is our initial value problem. Okay. Now, for the explicit method we have integrated from only within one interval. Okay. So, now for the implicit we are stretching to the left. Okay. So, we integrate x n minus j 2, that means more than one interval. It is more than, this is the interval of integration. Okay. So, then we get okay, right. Further, how are we going to approximate this f? If you recall, in the explicit method we have interpolated this using k past points. Okay. So, now that we are calling implicit, that means in the interpolation we need to consider n plus 1th point as well. Okay. Approximate f of x y by a polynomial that interpolates at k plus 1 points x n plus 1 x n So, please make a note, x n plus 1 is included. Okay. X n plus 1 is included. So, now similar to the explicit method, we have to use Newton's backward formula. Okay. So, let us use using Newton's backward difference formula with this variable, we are going to get, of course, kth degree polynomial, because we have k plus 1 points. So, I am not writing in terms of the x variable. So, directly I am writing in terms of u. So, this indeed okay. So, okay. So, this is a remainder term. So, again I am not giving the polynomial in terms of a variable x, because we have done it explicitly when we have discussed explicit multi-step methods. So, similarly one can do it. So, this can be left as an exercise. Okay. So, now this can be simplified as follows. So, the polynomial this is a remainder term. Okay. Now, as before, substituting 3 in 2, we get y of x n minus j. Look, the transformation and the, so here x n minus j. So, accordingly when we use the variable change of variable x minus x n by h is u, we get a different limit, that is minus j to 1 okay, plus t k plus 1. Okay. So, say t k plus 1 star okay, under the integral sign. Okay. So, further this can be simplified as, so now the approximation n minus j plus h, summation comes out, the quotes in this case so star within the integration, and if you remove the integration it is this. So, that is the notation I follow. Okay. Now, look at it. In the explicit method, if you could recall, we have defined gamma m 0 and in this case delta m j. So, what is the difference? So, it is only one interval. So, x n to x n plus 1, whereas here x n minus j to x n plus 1. So, that this is the indication, the length of the interval. So, if the length of the interval is just 1, we are using 0, and if it is x n minus j to x n plus 1, we are using j. Okay. So, now the polynomial becomes the approximation becomes where the quotes and this is the error. Okay. So, this is the error. Now, one can compute the quotes. One plus j one plus j square etc. So, for example, when we are using more than one interval to the left, if we fix a particular j, so that will determine the quotes. Okay. So, these are functions of j. So, for example, x n minus 1, n minus 2, n minus 3. So, depending on length of the interval, the quotes vary. Okay. Now, let us take a simple case, j is 0, that is again with a one interval. Okay. So, j equals to 0 case. If this is the case, where 1 etc. Okay. Accordingly, the approximation becomes okay. So, accordingly, this is the approximation. Now, what is the option in our hand? K. Okay. So, how many points we are using to interpolate the polynomial? Okay. Suppose we use 3 points that includes x n plus 1. So, we get a quadratic. Okay. Suppose these are known, then we get the polynomial as follows. So, this is f n. Okay. And the error T 3 okay. So, this method is called Adams-Moulton method. So, earlier one is Adams-Bashforth, that is explicit method, and this is Adams-Moulton method, implicit method. Why it is implicit? The implicit nature come from because in order to calculate f of, so this is implicit in this sense. Okay. So, we have two different concepts, that is, if the interpolating is including the n plus 1th point, then we end up with the implicit. If for interpolation, if we are not using the current point, only past points, then we end up with explicit. Okay. So, in general these are the popular methods. Okay. So, now for a given general multi-step method, how do we compute the error? Okay. So, well, this is the method, and then once we derive, we know this is the error, because we have derived it. But on the other hand, suppose there is a method given, we do not know what is the error. Okay. So, we have to compute. Okay. So, that means the coefficients, everything, somebody gives you, this is a multi-step method. So, can you verify what could be the error for this approximation? Okay. So, this is an important task, one has to learn. So, let us try to do that. Okay. So, that is local truncation error. So, we define T n plus 1 as minus the general multi-step method. We have given a standard notation. So, this is function values, past function values, and these are the derivative values. Okay. So, this is exact minus this is the approximation, right. See, what is this? This is exactly this is the method. Okay. So, if you take minus common, this term plus this is equals to y n plus 1. Okay. So, now expanding in Taylor series, let T n plus 1 be expressed as C 0 y of x n C 1 h Okay. That means, you expand this in Taylor series, then expand this in Taylor series, expand this in Taylor series. Okay. So, for a particular case we will do that, but in a general sense. Okay. See, for example, I can take an example and do it. So, see, for example, we need to expand n minus 2. So, this will be minus 2 h plus 2 h square y double dash of x n minus 2 h cube. Okay. So, in that sense, so for a general term I. So, for example, I is 1, then x n. So, a 1 y of x n. Okay. So, here y of x n, and here when I is 1 we get x n. So, what will be the coefficient from here 1 and from here a 1. Okay. So, it is like that, right. Suppose I is 2, then a 2 will be multiplying y of x n, because we have seen here y of x n coefficient is 1 and a 2 will be multiplying. Suppose y of x n minus 5, so what will be multiplying y of x n? A 5. Okay. So, that is how we get. So, therefore, if you take the difference and define it as T n plus 1 and expand in Taylor series, put it in this form, then we should try to identify these coefficients in terms of what? In terms of a I and b i's. Okay. So, this can be done as follows. Okay. C 0, what is C 0? Coefficient of y of x n. In this term coefficient of y of x n is 1, in this term coefficient of y of x n is a I, and in this nothing. Therefore, C 0 is 1 minus a I. Okay. So, if we do it in a general sense, we get slightly complex. Minus okay. So, this is C q, and we get quite complex expression for T p plus 1, which is the error. Okay. So, T p plus 1 we can write it So, it is quite cumbersome. It is not so much. If we understand the logic, that would keep us comfortable. Just that this is an error term and it is of this form. Okay. So, otherwise it is very complex. Okay. So, this must be of this form. Okay. So, when do we say a method is of so much order? Okay. So, the linear multi-step method as defined earlier is said to be of order p if C 0, C 1, C p equals to 0 and C p plus 1 is non-zero. How come? Look at this, the way we have defined local truncation error, exact minus the approximation, and that has been expanded in this form, and this is of order p if C 0 is 0, that means it agrees, this and this agrees up to p terms, right. C 0 rather p plus 1, C 0, C 1, C 2, C p, and from here C p plus 1 is non-zero, hence the error is coming from this term. Okay. So, that means in order to determine, we have to force each of this equals to 0 and solve the system. Okay. So, let us look at a specific case for how do we derive, okay, for a given problem, how do we determine the coefficients. So, example, derive a fourth order method of the form y n plus 1 a y n minus 2 plus h b y n prime plus c y n minus 1 prime plus d y n minus 2 prime plus e y n minus 3 prime and find the So, remember here y n minus 1, n minus 2, n minus 3. Okay. Okay. So, we have to expand each of them, right. So, let us start with, so we need for example, y n minus 2. So, this is y of x n minus 2 h y dash of x n plus 1 over factorial 2 h square y double dash of x n minus, okay, next y n dash keep as it is, then y n dash n minus 1 prime. Y dash of x n minus h y double of x n plus h square by 2 factorial y 3 of x n minus h cube by 3 factorial y 4 of x n, etcetera, and 2 . So, this is y dash of x n minus 2 h okay. Then 3 okay. Now, our method is this. So, what is our T n plus 1? Y minus h So, this was our T n plus 1 and this is written as C 0, this is written as C 0 y of x n, okay, plus C 1 h okay. So, we have expanded this, we have expanded, okay. So, the expansion of this then minus a y n minus 2 we have expanded. So, that is then minus h b y dashed of x n minus h c, this one we have expanded, then minus h d minus h e okay. So, now what we have to do? We have to collect for C 0, C 1, C 2 as powers of h power 0, h power 1, h power 2, etcetera. So, if you look at this, collect the coefficients of y of x n, this 1 there and minus a there, okay, right. So, if we do that, okay, that means collect the coefficients of equal powers of h. Okay. So, to start with h power 0, h power 0 is 1 minus a and there is no term. So, 1 minus a, this is our C 0 in fact, and we have to force it to 0, because we are trying to obtain a fourth order. Okay. So, remark is, in order to obtain a fourth order method, we need to force C 0, C 1, C 2, C 3, C 4, 0. Okay. So, h power 0, h power 1. Look, so h power 1, this is 1 here, then h power 1 in this case minus and minus plus 2 a, and h power 1. So, there is minus b, and here there is minus c, and there is minus d and minus e. Okay. So, I repeat again, h power 1, this is 1 plus 2 a minus b minus c minus d minus e. Okay. So, we get 1 plus 2 a minus b plus c plus d plus e. Okay. So, this is our C 0, this is our C 1. then H2, okay. H2, coefficient of H2, H square, look at it here 1 by 2. Now, here we have 4 H square. So, 2 get cancelled. So, 2 A. Okay. So, if you take 1 by 2 common, so coefficient is 1 by 2. So, here 1 by 2 if you take common, we have 4 minus 4 A, okay, minus 4 A. Then in this case plus C, because H square and minus minus plus, so just plus C. Okay. Then in this case H square, so that is 2 D, okay, 2 D, and in this case coefficient of H square is 3 E. Okay. Right. So, we get the following equation 1 by 2 if I take common 1 minus 4 A, from where this is coming, this is 1 by 2 common, 1 by 2 common. So, 1 from there minus 4 A, okay. Then minus C plus 2 D plus 3 E. So, how did we get coefficient of H square? See H square. So, minus minus plus and a C. So, this is H square, and here plus 2 D and here plus 3 E, that is what I have written. Okay. Then coefficient of H cube, look at H cube. So, 1 over 6, if you take 1 over 6 common, 1 there, and here H cube, H cube, okay. So, the next term is 1 over 3 factorial 2 H cube y 3. So, we have 8 H cube. So, if you take 1 over 6 common, minus 8 A. Okay. So, this is with a minus sign, sorry. So, this will be plus 8 A. Okay. So, 1 over 6 1 plus 8 A, because he is a, see it is alternating, right, minus 2 plus and minus. So, this must be minus. Okay. So, 1 over 3 factorial, that is 1 over 6 if you take common, 1 coefficient there, and here 2 cube is 8 plus 8 A. Okay. Now, look at the next, here H square and H cube minus half C, because 1 over 2 C, and here we have. So, if you take a half common, here we have C there, and here we have 4 D minus 4 D, and here we have 9 E minus 9 E. Okay. So, we get minus C plus 4 D plus 9 E. Okay. Now, H 4, H power 4, look at it here. Okay. So, 1 by 4 factorial. So, that will be taking common. So, coefficient is 1 there, then we need to extend this 1 over 4 factorial 2 H power 4 y 4 x n. Okay. So, here we have 8 there. Okay. So, this is a plus sign. So, minus 8a. Okay. So, if we take common, okay. So, that will be okay. So, this is 4 factorial. If we take common, we get so look at carefully. So, 1 coefficient, okay. So, then we 16. So, we have plus 16, right. So, this is minus 16a. Okay. So, we get 1 by let us do it. So, 1 by 4 factorial is 24, 1 there. So, 1 here, then 4 factorial taken common. So, this will be 16, yeah, minus 16a. Okay. So, then here h 4. So, this will be minus h cube by 3 factorial y 4. Okay. So, h 4 with a plus sign. Okay. So, this will be 6 1 over 6 c. Okay. So, this is plus 1 over 6 c. Then here this is 1 over 6 common, minus minus plus 8 d, 8 d. Okay. Then here we have to go for one more y 4 of x n. So, here 1 over 3 factorial common, minus minus plus 27 e. Okay. So, this is equals to 0, this is our C 4. So, the remark is since we are asked to determine a fourth order method, we need to force C 0, C 1, C 2, C 3, C 4, 0. Okay. So, now we have A, B, C, D, E. So, 1, 2, 3, 4, 5 equations. Okay. So, let us call this entire system. Okay. So, now on solving we get A. So, on solving this we get A equals to 1, you may check please, B is 21 by 8, C is minus 9 by 8, D is 15 by 8 and E is minus 3 by 8, and hence the method we obtain plus h by 8, 21 y n prime okay. And if we take the next terms, okay, so that means which is non-zero, C 5 81 by 240 H 5 okay. So, this is the fourth order method that we have been asked to derive. So, that means what did we do? We were given a multi-step method where the coefficients are not known. It was asked to derive a fourth order method. So, then what did we do? We have expanded each of the terms and then we have considered the residual, that is the difference between the exact minus the approximation, and substituted the expansions. Then we have collected the coefficients of equal powers of h and then we have determined the coefficients that will decide the matter. Okay. So, accordingly, if suppose somebody asks derive say third order method, then we expand and collect the coefficients of equal powers of h and force them to be 0 of C 0, C 1, C 2, C 3. Okay. And then C 4 onwards will contribute to the error, right. So, this is very important. This will give an idea of how the generally the local truncation error is computed, and if you do not know, just a multi-step method is given, and then what will be the error. So, the same method, and suppose you do not know the coefficients and then you are asked to compute a method of so and so order, and then also similar method we do, but then from the system of equations we try to make them force them to be 0 up to the desired order and solve the system to determine the coefficients and further determine the error. So, this gives a fairly a good idea of how in general either explicit or implicit multi-step methods are derived. Okay. So, now we have to discuss in coming lectures maybe some problems. Apart from problems, we have to discuss about some theoretical considerations like stability, convergence and things like that. Okay. So, until then, good day. Thank you. Bye.